Okay, so the recording should start. You are recording, and I'm going over to share the screen. And hopefully you can see the screen. Can you see the screen? Wonderful. Let's hope that for the last few sessions, Teams will play nicely with us, and then, all is good and we can all relax. Because it's been quite an interesting term, hasn't it? I mean, to be perfectly honest, I've never seen anything like that, and I'm in the business for over 25 years. And thank you very much, Bernardo. The obligatory link. And I think we probably at one point should give Bernardo a big round of applause for doing all the linking. That's really, really great stuff. So a virtual applause to Bernardo. You are a good person. Yeah. I clap on your behalf. Wonderful. Okay. And I think somebody has their microphone on. So do a clap and then please mute. Or is that me? Ah. Yeah, my mic is on. I hope so. In the form of currency. Or pizza? How about pizza? Okay, so shall we get started? Because we have to do a little bit. I knew that. We've got a little bit more work to do. And what I want to do with you today is really expand on what we have done. What we have done in the last few lectures. We discussed the last time special order reactions, and I showed you how we can calculate 0, first and a little bit of second order reactions. So yes, and please don't forget to record your attendance on Moodle. I know it's one of the last days, but they are a bit funny. So what we have dealt with was, if we have a reactant, let's call that A, and this is consumed, we can write the general rate law, the change in the concentration of A over time equals minus K times the concentration of A to the power of, let's call that M. Whatever we want to call it. And can you please mute your microphone? That would be great. Can anyone else hear me? Is this a general problem that Elena reports, or is it hers? Daria says yes, you can hear. Okay, good. Then I'm not entirely sure, Elena, what the issue is. Might be your end. Log in again, and that might solve the problem. Okay, so that was the reaction that we discussed, and I showed you if, for example, m equals 0, we have a 0-order reaction, we would plot the concentration of A versus time, and we would probably get something like that. We can't get anything negative, and the gradient here, this gives us minus k. Thank you guys. That's a very helpful tip. Hopefully Elena can sort out this thing. I didn't know that. So we also looked at m equals 1, and we found that we can calculate the final concentration. A final equals the initial concentration times e to the power of minus k times T final minus T initial. And we can use different forms of this equation. And when we plot this thing, then we would get, if we just simply plot A versus time, we would get a curve like that. And if we then plot Ln of the concentration of A versus time, we would get a straight line. This point here would be Ln A initial, and this line can also go into the negative range. And again, the gradient here would be minus the rate constant. And this is dt at the top, yes. Or you could say this here would also be our time difference, yes. Although it would not be a very small difference, this would usually be a larger difference. So one could write this as capital delta T. But I think that's just a formalism. Okay, so this is what we got. And I think we need to and how would you tell the difference between them? Well, in one case, you would calculate them. You would have some data, for example. So you would have time, and you would have concentration of A. So you would measure that. You would have that, and you would measure A. And if you plot that directly, you would get this curve. But if you calculated Ln of these data and plot that, you would get this. So it's rather straightforward and nothing to worry about. So that was all for the reaction of A is consumed into something. However, as you can imagine, life is not always that easy. And I think Edith pointed out at one of the previous sessions that sometimes we not only have one reactant, we might have more reactants. We might have, say, A plus B plus C, and they all react. And form whatever products we might get. So how on earth are we going to deal with that? How can we write any rate laws for that? Now let's think about it, what this actually means. It means the reaction takes place and we would see changes in all three concentrations. We would see changes in A, B, and C. So we can write this general rate law if we've got a case like that with several components, with several reactants. We can write the change in A per time unit would be the same change in B. because A requires B and requires C, and B requires A and requires C, and C requires A and B. So the changes would all be the same. dA over dB, dA over dt is the same rate with which B disappears, dt equals dC over dt. So these rates are all the same. And we can write them as negative k times. Well, what does it depend on? Well, surely it depends on the concentration of A. Let's say this is to the order, to the rate order of, let's call that A, lowercase a. And it also depends on the concentration of B, also has a rate order and let's call that B. And it depends on the concentration of C. So let's call that rate order C. So this is here a very general rate law if we have several reactants. So we can write a general rate law. It has only one rate constant because we can combine all rate constants constant into this one here. So that would be a combined rate constant, but nevertheless it is a rate constant. Combined rate constant. And each component has its own individual rate order. And Charlotte asks, what if a molecule is not directly involved when it is, for example, an enzyme or something like that, that catalyzes the reaction but is not used? Well,
do you reckon they're going to release like 10?
Sorry? Okay. Yeah. Okay. If it is not involved, then either we can leave it out, it doesn't play any role, or it has a role, and we will discuss that, what this role could be, and how we implement that at a later point, in a different module, actually. But we will come back to that. So we have combined rate orders, and we have the rate constant, and we have the individual rate orders. So A, B, and C. These are the individual orders. Rate orders. Somebody has just fallen off their chair. Are you all right? Yeah? Oh, that's good. Now, actually, we could say, what order is this reaction? What order is this reaction? Yeah, they were really shocked. What order is the reaction? We can't know. Yes, we do know. We can know, actually. We can say, we can give it an overall rate order. An overall rate order. And the overall rate order is just simply the sum of the individual rate orders. In this case, A plus B plus C. Absolutely right. And it really depends on what the individual rate orders are. So all we need to do is we have this reaction as A plus B plus C. That's the overall rate order with individual rate order of, whatever A, whatever B, whatever C is. And as I said before, the order of a reaction is just simply a mathematical concept that makes this equation, this general rate law equation, a valid equation. So, for example, we have minus K times, so let's say dA over dt equals minus K times A to the power of 1 times B to the power of 2 times C to the power of 3. So the overall rate order just simply would be, well, 1 plus 2 plus 3 would be 6. So that's the overall rate order with a first order in A, first order, with a second order in B, and with a third order in C. Does it make sense? But of course, these numbers don't have to be whole numbers. They can be fractions, they can be integers, they can be whatever you want. They can be even negative numbers. So you could end up with a reaction dA over dt equals minus K times A to the power of 1 times B to the power of negative 1. So the overall rate order in this case would be what do you have? The overall rate order for this one would be a zero order reaction. The overall would be 0. But the individual rate orders are different. The individual rate order for A is 1, and the individual rate order for B is negative 1. But the overall rate order would be 0. Are you happy with that? It's not terribly difficult. A few years ago, I did an example where the overall rate order was 5. And then the students did some practice calculation, and they, just by sheer luck, the overall rate order in the practice calculation came up as 5. So I then also asked asked a similar question in an exam, and some students where the numbers were 3, 4, and minus 1. And yes, you can get a fractional rate order. It doesn't. As long as it is a number, you can have that as a rate order. So I asked them, what is the overall rate order in this case? So 3, 4, minus 1 would give you a rate order of 6. And about 10% of the students actually wrote down the overall rate order is 5. And I thought, what? Why is it 5? No. Well, it turned out, after a lot of detective work on my side, that the students believed that the overall rate order always has to be 5. So there was a slight misunderstanding, which made me laugh. So the overall rate order is the sum of the individual rate orders. It can be any number. And all you need to do is to get the overall rate order, you just simply calculate You just simply calculate, you add up the individual rate orders. No, it's not the slowest part. It is actually, in this case, the rate order all combined. And I'll give you an example for that. Let's say we have dA over d. No, let's write it in a different way. We have A plus A reacts. So we can write dA over dt equals minus k times, and in this case, A square. So what's the rate order for this? It's a very simple question. It's 2, absolutely. Okay, let's write A. And we have actually dealt with that. I showed you how we can calculate it. It would be 1 over A final equals 1 over A initial plus K times T. And I showed you that in the last session. So we can integrate that, calculate that, and end up with this equation. Now let's do this one here. A plus B, and we would get dA over dt equals minus K times, let's say that is a first order reaction, and this one is also a first order reaction. What's the overall rate order for the A plus B? It's also 2. Absolutely right. So here we have got 2. And here we've also got 2. But trying to solve this one here is not impossible. Not impossible. But very, very difficult in terms of integration. It's very, very complex, and it's certainly beyond our means. Right. So we have, in both cases, we have a second order reaction, but the reactions are very different. And one we can easily solve. That is if we've got the same reactant twice, but if we have different reactants, it's incredibly difficult to actually solve that. Now, we have always looked at the reactants. So we looked at A is converted into something. But of course, you might ask, what happens to the product? Let's just simply call that, in this case, let's call that B. So A is the reactant, and B is the product, just as a little bit of terminology. So we certainly can write dA over dt equals negative K times A concentration of A to the power of, let's say, M. Again, that's our general rate law. That describes A. So, but what happens to B? dB over dt. How can we describe that? Now, instinctively, you would say, right, we produce B, so because we've got this case here, we produce B, and therefore, instead of writing minus, like we've done before, we would have to write positive K, and it would be absolutely right, it would be positive K instead of minus K, times. Now, instinctively, we would write, well, it depends on the concentration of B. But that's not true, because the production of B, of this one here, does not depend on the production, on the concentration of B. It actually depends on the concentration of A. So in this case, we still have to write A to the power of M. That is just simply because B doesn't depend on its own production. It still depends on what is delivered from A. So we have for the change in B, and we change the sign because we now produce something. If we consume, like in the case of A, we have a negative sign. If we produce something, we have a positive sign. I'll come back to that in a moment. Now, how can we... Oh, somebody's unhappy. So how can we actually solve this equation? dB over dt equals k times a to the power of m. How can we differentiate and integrate this thing? And the answer is we can't. We cannot integrate that. So that's a little bit of a bummer, isn't it? But wait a moment. Wait a moment. What we can do is, we can say, for example, let's look at the exam scripts again. I start with 100 scripts, 100 unmarked scripts. Okay, and then over time, I convert them into marked scripts. With whatever rate constant, whatever rate order I use. Let's call this is my starting AI. And this here, that would be the product. This would be my B here. How many marked scripts can I maximum have? How many marked scripts are possible for me? Absolutely right. So I can get a maximum of 100 scripts. How many unmarked scripts would I have left if I had 100 marked scripts? I would have 0 unmarked scripts left if I have 100 scripts. So can we write this in a slightly different form? I can write this as my, or let's say, what happens if I start with 100 unmarked script and after a while I have 60 unmarked scripts? How many marked scripts do I have? If I have 60 unmarked scripts, 40. Yep, that's right. 40 marked. Do you see what's happening here? This would be my concentration of unmarked script at the time, and this would be my concentration of marked scripts at the time. And what we can see is A final plus B final gives me my A initial. So if I have, let's say, 30 scripts left, and I started with 100 scripts, how many scripts would I have marked, my BF? Absolutely right, it would be 70. So A final plus B final always gives me my A initial. Now let's see how this would look like. So here we would have, let's say, A. Here we would have time. Let's say we have something like this. That is for A. So A, the unmarked scripts, the unmarked scripts are going down. That's my A initial here. And what does my B do? I use a different color. So I start with no marked scripts. And I would get a curve like this for B. And if I add them up, this one plus this one gives me this one, gives me my A initial. Or this one plus this one gives me this one. Or I can say this number here plus this number here also gives me my A initial. Do you get that? It's basically exactly the same what we've done with the marked and unmarked script, but we just simply use a graph for that. So what can we do with that? We can say we have a relationship between these components. And let's say we have a first order reaction for A. What we can do is we can say, right, B final equals, I bring this to this side, equals A initial minus A final. Yeah? This is basically how you calculated how many marked scripts I have. It was 100 minus 60, for example, here, and I got 40 marked scripts. Yeah, so that's this equation. Now, the great thing is, I know how to calculate A final if it is a first order reaction. For a first order reaction, we said we can calculate first order reaction. A final equals A initial e to the minus k times t, basically, or delta t if you want. So what we can do is we can say B final equals A initial minus A initial e to the minus k times t. Or if I want to, I can factor A initial out. B final equals A initial times 1 minus E minus k t. So This is actually the equation, the first order equation for not the reactant, but in this case, the product. Well, if you want, you can write this T as the difference of T final minus T initial, but usually you would say T initial is 0. And very often you just see it in this way of writing, where people just simply say our starting time point. We are not so much interested. We are just simply, we denote the difference in the times with a T. That's why I also have this T here like that. Strictly speaking, you would need to call this T final minus T initial here, but usually people say T initial equals 0. So that would be the equation for our product. So when I told you we cannot integrate this equation here for the product, it's still true, we can't integrate it, but we can work around it, and we have a nice equation. So a little bit more complicated than our original equation for the first order reaction for the reactant, like this. But it's not terribly complicated in this case. So this shows how we can actually calculate the product in a reaction. If we have a relationship between the initial starting points, then we can work around this unintegratable calculation, and we can come up with, for example, for first order reaction, with this equation. And the one comes because I factor out A initial. I take that out, and if you multiply it in again, 1 times A initial gives you A initial times this term gives you A initial times E, and so on. So that's where this 1 comes from. Right, now we learned how we can calculate something like that. No, it's not. It depends on the actual reaction. I just wanted to show you here for a first order reaction, because that's one of the most common problems that you will encounter when you do a little bit more advanced kinetics. And if you do, for example, a zero order reaction, again, it's very easy to do that. For a zero order reaction, you have T, you have the reactant A, so that would be A, and for B, you would have something like that for B, where you again can add them up, and they always give you the A initial. So you could add them up here. So it really depends on the order, but you can, with this relationship, you can always convert that quite nicely and easily. So I'd really like you to sort of appreciate this equation, how we can calculate B. Now, hey, tell you what, let's have a little bit of fun with these things, right? Let's do a weird one. Let's say we have a reactant of A, and this is transformed into B. Let me write this B nice, because otherwise I get a complaint that people can't read my handwriting. B. And we say we have a rate constant of K sub 1. Okay? And now, let's say we have a reaction in the opposite direction with a different rate constant of K, let's say, sub -1. Or you can call it 2, or you can call it whatever you want. I prefer 1 and -1 because if things get more complex, you know that these Ks all belong to, let's say, the first step in a reaction. So how can we calculate our final concentration of A? That's interesting, isn't it? How can we calculate our final concentration of A? So we know that, well, we can actually break that down. We can break it down into the first reaction, K1 sub 1 into B. And we know how we can calculate that. So that would be dA over dt equals minus K1 times A to the power of, say, A. And we can also break it down into the other reaction, BA. And here we have K sub -1. So that's the reverse reaction. And here we have dA over dt equals plus K, Peter, write it properly, plus K -1 times B to the power of B. That is what we just discussed up here. So what is now our true rate? Well, obviously, we have reaction going from left to right and from right to left. So all we need to do is we say our change in A over time is nothing else but the sum of these two reactions. So it would be minus K, A to the power of A, plus K for the reverse reaction, B to the power of B. You don't need to put in the minus, the sub negative minus into a calculator, because these would be numbers. This is just me writing to indicate that these are two different rate constants, but they all belong to the same reaction. That is what this actually means. So our overall change in A depends on how fast it is consumed. That's the first bit. That's the consumption bit. Plus how fast it is produced. They're just subscripts. Thank you very much. That's what I wanted to say, but you are far more eloquent, Reynolds. Thank you. So our change in A depends on the consumption and the production of A at the same time, of course, because it happens right here, right now. What happens if consumption is the same as the production? What happens if this part here is the same as this one here? What do we get in terms of A or change in A? If they are both the same. Edith, you're absolutely right. dA over dt. In this case, if consumption is the same as the production, we get a 0. What does a 0 in this case mean? 0 means there is no change in the concentration of A. So the concentration of A does no longer change in this case. And we can say minus K sub 1 A to the power of A plus K sub negative 1 B to the power of B equals 0. And as people said, Joby and Edith said, this has a name. This is the equilibrium. At an equilibrium, the changes in the concentrations are 0. It's not the concentrations that are 0, it's the changes in the concentrations are 0. Tell you what, we've got a beautiful equation here. Let's expand that a little bit. Let's bring that thing with the negative to the other side. So we have K sub negative 1 B to the power of B equals K1 A to the power of A. This is our equilibrium, right? Now, tell you what, why don't we put everything with concentration to one side and everything that doesn't have a concentration to another side? Let's put this to this side and this to this side. We would get B to the power of B, the rate order, divided by A over A equals K sub 1 divided by K negative sub negative 1. So we have our reaction A to B, and you know you can write this equilibrium as an equilibrium. You can write this as concentration of B, and usually you would do that as B over A equals your equilibrium constant. Hey, look at that! What we've got here. We've got the equilibrium constant for this reaction our equilibrium concentration is nothing but the ratios of the forward and the reverse reaction. And that's exactly where the equilibrium constant comes from. Edith, you are absolutely right. So the equilibrium constant, this KEQ, is nothing else but the ratio of the, I call this the forward reaction, and that would be the reverse reaction. So here, that is the forward and that is the reverse reaction. So you see, at equilibrium, there's no change. The equilibrium is defined by an equilibrium constant, KEQ, and this equilibrium constant is nothing else but the ratio of the two different rate constants. Isn't that mind-blowing? I think this is just absolutely wow. But it gets better. We've got 5 more minutes. It gets better. What about the following? We have a reaction, and A is converted into B. But now we have a biochemical pathway. B is then consumed into something else, C or something like that. So let's say K1. This is another reaction. We've got K2 here. So what can we write? dA over dt equals, well, that's easy. We just have to look at one thing, is minus K1 times A to the power of A. Now for B, we have something more interesting. The change in B over time depends on the delivery from A, from this reaction. So we can write plus, because it's produced, K1 times A to the power of A, minus, that's now the consumption, minus K2 times B to the power of B. Do you see that? What happens now if this part, the production, is exactly the same as the consumption? What do we get for the change in B? Absolutely right. What do we get if production and consumption are exactly the same? If they are the same, we get dB over dt equals 0 again. Look at that. We've got 0 again. There's no change in B. When we have this situation, so we can write, in this case, K1 A minus K2 B equals 0. We bring that to the other side. We get K1 A to the power of A equals K2 to the times B times to the power of B. We put everything in order, so we get K1 over K2 equals EB over A to the power of A. Now look at that. This looks exactly like our equilibrium constant here, doesn't it? Looks exactly like our equilibrium constant for this condition. Is it an equilibrium? What do you think? Should we call that an equilibrium? This case, our toy biochemical pathway. Is it an equilibrium? If it's 0, it is a yes. There's no change in concentration. I absolutely agree with you. So if I did a vote, a poll here, people would argue that, like Edith said, there's no change in concentration in B, and therefore we should call it an equilibrium. But people are a little bit careful, because an equilibrium, when we're talking about an equilibrium, it would be a situation where we have something like that. That is when we have the equilibrium. What we have here is this one here. So strictly speaking, it's not an equilibrium, but conceptually it is an equilibrium, and it just has a different word for it. This is actually called the steady state. If there is no change in concentration, no change in the concentration of B, then, and we have this condition here, if there's no change in concentration, the system has is sort of not necessarily an equilibrium, because it is not an equilibrium. Equilibrium would be forward and reverse reaction. It just simply has a different name, and instead of equilibrium, we can call that the steady state of the system. Conceptually, it is an equilibrium, but the correct term for that would be a steady state. Does that make sense? Good Lord, you have done a lot of hard work. So I think in the next few lectures, I will go easy on you. And I think what we're doing tomorrow is I will give you an application about these kinetics, which hopefully will give you... Oh, I'll tell you tomorrow. Let's do another cliffhanger. Anyway, time's up. Thank you very much for listening. And don't forget, for those who are doing BI 300, we're going to have a session this afternoon on the history of DNA discoveries. And I'm really looking forward to seeing you in this session if you want to know more about sex, crime, and betrayals in the discovery of DNA. See you later or tomorrow. Have a lovely day. Bye-bye.